next, integration. So here's the idea of integration. Why do we care about sets of equivalent hydrogens? Because each set of equivalent hydrogens should give a separate signal in the NMR. So when we look at our NMR spectrum, if I have 5 sets of unique hydrogens, I should have 5 signals in my NMR. Now I call them signals because when we get to splitting, we'll see that a signal can be split up into multiple peaks, but they come together. So it's this group of peaks. What integration then says is, this is something that comes from the fact that NMR instruments were first invented by physicists, or let's say, really organic, or they were invented by chemists / physicists that understood a lot of physics, and a lot of physics is very mathematical based. So I don't know how many of you have had calculus, and if you haven't, you don't need to worry about it. But in calculus, we do something called integration, and integration is basically you plot a curve and then you measure the area under that curve. So here's an example of 2 curves. So what we're basically saying is it's the area in that section of the curve. And if you haven't taken calculus, if you do ever take it, you'll see that that's the physical interpretation of that mathematics. That's what that thing is giving us, the information it's giving us. In the NMR then, the key here is that, can you guys see that? So I was going to give you an example of integration, and I don't know why I got lost. So I've already written it out. This is a really simple molecule. It's ethanol, right? There's 3 sets of equivalent hydrogens. Let me just sketch what the NMR would look like for this. Not going to be perfect, but it'll be close. I'm sort of trying to exaggerate here, or like really show it. And then somewhere in this region, I'm just going to do it right here, is going to be a blob. Now, what this represents then is, I'm going to put my labels next to them. This is why we label them. So now we can say, here's hydrogens B. This is the signal for hydrogens B. This is the signal for hydrogen C. This is the signal for hydrogens A. They're probably not to scale. This would be what they would look like in a really weak NMR. As I said, in a really weak NMR, the peaks are kind of broader. In a more powerful NMR, they'd be like a lot closer together and a lot narrower. What we would see is that hydrogen C is only 1 hydrogen, right? So the computer would calculate a number for that area, okay? And that number might be something like, let's say, let me pick something that's not ridiculous, but that is not quite so straightforward. Let's do 45, right? In other words, there's going to be units or something. It's going to calculate a number. So this one, if that has an area of 45, this would be an area of 90. And this would be an area of 135. Now you're looking and saying, what does that mean? Where those numbers are off the wall. Those are just like you measure the area. That's the area, right? But what's important is the ratio of those areas, okay? That makes sense? So in other words, what we do is we find the smallest one, which is 45, and we divide them. So do you see that's a ratio then? So this one, for example, is 2. This one is 1. This one is 3. Do you see? So those ratios give the ratios of the number of equivalent hydrogen. Now, sometimes when you do this, you get a ratio like 1.5. To get those to work out, you have to have them all be whole numbers because you can't have half a hydrogen. So you'd multiply all those ratios by 2. Those would be the actual number or say of equivalent hydrogen. Does that make sense? Now, when we do this then in the actual NMR, there's 3 different ways we can be presented with integration data, from hardest to easiest, okay? So the first one is the hardest, where you're just given the numerical values for the area that was calculated by the computer. Then you have to do the division, and then you have to get them into whole numbers, and then you also have to figure out if there are symmetries that cause those to be multiples of those whole numbers. The next easiest would be to be given the ratios, but not guaranteed that it's the actual number, because the actual number could be a multiple of those ratios. Kind of like molecular formula and empirical formula, right? Empirical formula is the lowest ratio. Molecular formula is then maybe it's a multiple of those. And then finally, you could be given the actual number of hydrogens. And usually in the NMR, if we're indicating not the ratio, but the actual number of hydrogens, we put the letter H after it. So if you're just given like 2, 3, and 1, you're not guaranteed that there are exactly 2, 3, and 1 hydrogens. You have to look at other information. But if you're given 2H, 1H, 3H, you're guaranteed that that's how many hydrogens there are in that giving that signal, in that set of equivalent hydrogens giving the signal. So that's integration. Any questions about that?
I was just wondering, Professor, why when you draw the B set, why did you put 4 peaks?
Because of splitting. So we'll get to peak splitting in just like 5 or so minutes. But what happens is when equivalent hydrogens like hydrogens A, see, sometimes we do that. We circle them all out and say those are all the same. They are adjacent to a carbon with other set of hydrogens. So this is hydrogens B, right? A and B, their signals interact and they split, they become split. So instead of being one peak, they split into multiple peaks. But they're all peaks, all part of the same signal, just a signal that's chopped up into smaller chunks, okay? That's why I use the term signal, right? So this whole thing, this is a signal for hydrogen B, and then these are actual peaks. You see the difference? So the only signal that's going to give just one peak is this one, which doesn't split. And we'll talk about why that's the case. It's a special example. I'm going to give you just a rule today, but then I'll explain it tomorrow. Okay?
Dr. M, quick question.
Yeah.
Say you're to add another CH2 in between, right, for this example.
So let's say...
it was CH3, CH2, CH2OH.
Okay, so like one propyl instead of...
Yeah.
Okay.
Are those... The CH2 hydrogens are no longer identical, right?
That's correct. So we would have A, B, C, and D.
And then those will also have different signals on the NMRs that will show up.
That's correct. They'll come at different locations because their electron densities will be different.
Right.
And they'll be split differently. So this one in particular is going to be split up into a lot more peaks. It's going to actually be split up like this. Be split into 6 peaks, okay? Because of the number of adjacent hydrogens, and we'll talk about that.
Right.